Right now, 1 billion kilometers from where you're listening, a system of ice and rock circles a distant world in perfect silence. Saturn's rings stretch 282,000 kilometers from edge to edge, yet they rise only 10 meters thick in some places. They've been there for tens of millions of years, possibly hundreds of millions, catching sunlight and casting shadows across clouds of hydrogen and helium. They exist, they're real, and Earth has none. But the physics that built those rings doesn't belong exclusively to Saturn. Gravity follows the same mathematics everywhere. The forces that shattered moons and captured debris into elegant bands around that distant planet would work the same way here. Earth has sufficient mass. Earth has sufficient gravity. The only thing Earth lacks is the material, suspended at just the right distance, in just the right orbit, ground down to just the right size. Everything else about our planet would permit rings to exist if they had formed, if they had been captured, if some cosmic accident had placed them there during the right window of our planet's long history. This isn't speculation about exotic physics or alternative realities. This is simply asking what would happen if the same verified, observable, measurable phenomenon that exists at Saturn existed here instead. The question isn't whether it's possible. Rings around planets are common throughout the solar system. The question is what it would look like, what it would do, and how it would change the experience of looking up. Tonight, we're going to explore that question slowly. We're going to build a picture of Earth with rings using only confirmed physics, verified measurements, and the actual properties of planetary ring systems that we've studied for decades. We'll move through each aspect carefully, examining the view from different places, the effects on light and shadow, the subtle changes to tides and seasons, and the quiet persistence of billions of particles held in orbit by nothing but gravity and momentum. You don't need to do anything but listen. You don't need to visualize unless you want to. You can simply let the information settle gently, fact by fact, detail by detail, building a coherent picture of something both strange and peaceful. There's no urgency here, just a slow exploration of what would be different and what would remain exactly the same. The journey will take us from the basic physics that govern ring formation through the visual reality of what rings would look like from different latitudes and times of year, into the effects on Earth's environment, and finally to the implications for human history and our modern relationship with space. We'll cover each topic with enough depth to understand it properly, and we'll take our time doing so. So, settle in wherever you are. Let your thoughts slow down. And let's begin with the fundamental question of how rings form in the first place, and why Earth could support them. Planetary rings aren't mysterious. They're not held in place by exotic forces or unusual physics. They exist because gravity behaves differently at different distances, and because objects can orbit stably within a specific range around any world massive enough to hold them. The key concept is called the Roche limit, named after Édouard Roche, the French astronomer who calculated it in 1848. The Roche limit is the distance from a planet where tidal forces become stronger than the gravitational force holding a smaller body together. Move a moon or asteroid closer than this limit, and the gradient in gravitational pull across its diameter will overcome the gravity trying to keep it intact. The near side gets pulled more strongly than the far side. The object stretches. Then it breaks apart. For a rigid body, something with internal structural strength like solid rock, the Roche limit is closer to the planet. For a body held together only by its own gravity, like a loosely bound pile of rubble or a moon made of ice and rock, the limit is farther out. The exact distance depends on the densities of both objects involved, but for Earth and a moon-like object with density similar to our actual moon, The Roche limit sits at approximately 15,600 kilometers from Earth's center. That's about 2.4 times Earth's radius. Our moon orbits at 384,000 kilometers. It's nowhere near the Roche limit. It never has been. But if a moon or large asteroid had wandered into that inner zone during Earth's early history, or if tidal forces had gradually pulled an existing moon inward over millions of years, it would have crossed that threshold and disintegrated. The fragments wouldn't fall to Earth immediately. They'd remain in orbit, each piece following its own path, colliding gently with neighbors, grinding down over time into smaller and smaller particles. Eventually, through a process that takes millions of years, those particles would spread out into a thin disk, all orbiting at slightly different speeds, all held in place by the exact balance between their orbital velocity and Earth's gravity. That disk would be Earth's rings. Saturn's rings may have formed this way. One hypothesis suggests they're the remnants of a moon that ventured too close, or that was shattered by an impact sometime in the past few 100 million years. Another possibility is that they're leftover material from Saturn's formation, debris that never coalesced into moons because it was too close to the planet. The truth is still being investigated, but both mechanisms are well understood. Both rely on verified physics. Both would work around Earth just as well as they work around Saturn. The rings wouldn't be solid. They'd be made of countless individual particles, each one a separate object in its own orbit. At Saturn, ring particles range in size from grains of dust smaller than a micrometer to chunks the size of houses, several meters across. The vast majority are small, though. Most are between 1 centimeter and 10 meters in diameter, and they're composed almost entirely of water ice, 99% or more, with trace amounts of rocky material mixed in. The ice is dirty ice, not pure, stained slightly by dust and organic compounds, giving Saturn's rings a subtle color that's not quite white, not quite gray, with hints of tan and pale pink in certain regions. Earth's rings would likely have similar composition if they formed from the breakup of an icy moon. If they formed from rockier material, something with composition closer to our moon, they'd be darker, less reflective, composed of silicate minerals and metals rather than ice. The exact appearance would depend on the source material, but the structure would be the same. A disk of particles spread across thousands of kilometers of space, confined to a plane aligned with Earth's equator, held together by orbital mechanics. The particles wouldn't be distributed evenly. Rings develop structure. Saturn's rings have gaps, caused by orbital resonances with Saturn's moons. A particle orbiting in one of these gaps completes multiple orbits in the exact time it takes a moon to complete one orbit. Each time they align, the moon's gravity tugs on the particle, always in the same direction, gradually pulling it out of that orbital path. Over millions of orbits, this clears out a gap. Saturn has dozens of these gaps, the most famous being the Cassini division, a 4,700-kilometer wide space between the two main ring sections, cleared primarily by resonance with the moon Mimas. Earth doesn't have multiple large moons to create these resonances, but our single moon would still affect the ring structure. Its gravity would create waves, density variations, subtle patterns in the distribution of ring particles. The rings would have texture, not just visually, but in their actual physical structure. Some regions would be denser than others. Some would contain larger particles on average. The rings would be a dynamic system, constantly evolving, particles colliding and changing orbits, the whole structure held in a kind of equilibrium by the competing forces of gravity, momentum, and the tiny pressure exerted by sunlight itself. Yes, sunlight exerts pressure, It's small, but it's real. Photons carry momentum. When they strike a surface and are absorbed or reflected, they transfer that momentum. For ring particles, especially small ones, radiation pressure from the Sun can slightly alter their orbits over time. It's one of many subtle forces that shape ring systems, along with electromagnetic effects from charged particles in the planet's magnetosphere, drag from the outermost wisps of the planet's atmosphere, and the gravitational influence of any moons that happen to orbit nearby. All of this is established science. None of it is theoretical. We've observed these processes at Saturn, at Jupiter, at Uranus, and Neptune. We've watched ring particles collide in images from the Cassini spacecraft. We've measured the composition using spectrometers. We've calculated the orbital mechanics and confirmed our predictions with direct observation. Planetary rings are well-understood systems governed by well-understood physics. Earth lacks rings not because rings are impossible here, but simply because the events that create rings haven't happened here. Our planet didn't capture a moon in the right place. No moon has spiraled inward and broken apart. The debris from the giant impact that likely formed our moon ended up coalescing into the moon itself, not spreading into rings. These are accidents of history, not fundamental differences in planetary physics. If Earth had rings, they would behave according to the same principles that govern Saturn's rings. They would orbit in the equatorial plane. They would be thin, possibly only tens of meters thick despite stretching across thousands of kilometers horizontally. They would reflect sunlight, they would cast shadows, and they would be beautiful in a way that's difficult to describe, not because beauty is subjective, but because rings would be unlike anything else in our daily experience. A permanent arc across the sky, visible from half the planet, changing appearance with the seasons and the time of day, always there, always silent, always in motion, even though they'd appear perfectly still. Let's consider where these rings would be precisely. The Roche limit for Earth is approximately 15,600 kilometers from the center, as mentioned earlier. Earth's radius is 6,371 kilometers at the equator. Subtract that, and the inner edge of stable ring formation would begin about 9,229 kilometers above Earth's surface. That's higher than GPS satellites, which orbit at roughly 20,000 kilometers, and much higher than the International Space Station at 410 kilometers. But it's well within the region where ring particles could orbit stably. If we follow Saturn's proportions, Earth's rings might extend from about 9,000 kilometers altitude out to perhaps 80,000 kilometers, spanning a width of 71,000 kilometers. At that distance, the rings would subtend an enormous angle in the sky when viewed from Earth's surface. From the equator, looking north or south, you'd see the rings edge on as a thin, bright line rising straight up from the horizon. From mid-latitudes, you'd see them at an angle, arcing across the sky from horizon to horizon. From the poles, you'd see them face on, a complete disk surrounding the planet, though you'd have to look down at the horizon to see them since they'd be confined to the equatorial plane. The rings would orbit with the same period as objects at their particular altitude. At 9,000 kilometers, orbital period would be approximately 3 hours. At 80,000 kilometers, about 25 hours. But you wouldn't see them rotating. The rings are made of billions of particles, each moving independently, and their collective appearance would look stationary, just like Saturn's rings appear stationary in photographs, even though the particles are traveling at tens of thousands of kilometers per hour. From Earth's surface, the rings would seem motionless, a permanent structure, unchanging except for the way sunlight illuminates them and shadows cross them. This is the foundation. This is the established physics and the confirmed measurements that would determine what Earth's rings would look like and how they would behave. Everything that follows builds on this base of verified scientific knowledge. And now that we understand what rings are and where they'd be located, we can explore what they would actually look like if you were standing on Earth's surface, looking up. Imagine stepping outside on a clear day. The sky is blue, the sun is shining, and directly overhead, cutting through the atmosphere from one horizon to the opposite horizon, is a band of brilliant white light. It's narrow, perhaps a finger's width from your perspective, but it's unmistakably there, brighter than clouds, steady and permanent. This is what you'd see from the equator if Earth had rings. At the equator, you're standing on the plane where the rings orbit. You're looking at them edge-on. Despite stretching thousands of kilometers from inner edge to outer edge, the rings are extremely thin, perhaps only 10 to 100 meters in vertical thickness. From your position directly below them, you'd see only that thin edge, but it would be brilliantly illuminated by the sun. The ice particles making up the rings would reflect sunlight directly down toward you, creating a bright line in the sky. The line would stretch from the northern horizon to the southern horizon, passing directly through the zenith, the point straight above your head. It would remain in this position always because the rings orbit in Earth's equatorial plane and you're standing at the equator. Turn east or west and you'd still see the line running north-south. Walk north or south and the line would appear to tilt, no longer passing straight overhead. The brightness would vary. Near the sun, the ring would be harder to see, washed out by glare and atmospheric scattering. But away from the sun, especially near the opposite horizon, the ring would glow distinctly against the blue sky. At sunrise and sunset, when the sun is at the horizon, the rings would catch the light and glow brilliantly, visible from one side of the sky to the other, painted orange and red by the same atmospheric scattering that colors our sunsets. Now, move north. Travel to 20 degrees north latitude. The rings would no longer pass overhead. Instead, they'd arc across the sky at an angle rising from the southern horizon, reaching maximum altitude of 70 degrees above that horizon, then descending back down. From this latitude, you'd see the rings not edge-on, but at a slight angle, and this changes everything. When you view rings at an angle, you see their width. You see the actual structure of the disk. The thin line would broaden into an arc, still bright, still white or pale blue depending on lighting and composition, but now visibly wide, perhaps several degrees across as measured in the sky. The rings would have visible texture, brighter regions and darker regions. The gaps and divisions in the ring structure might be visible, thin dark lines cutting through the brightness. At 45 degrees north latitude, roughly the latitude of cities like Milan or Montreal or Portland, the rings would arc across the southern sky in a grand sweep. They'd rise about 45 degrees above the southern horizon at their highest point. The arc would be wide, substantial, unmistakably three-dimensional despite being projected on the dome of the sky. During the day, they'd be bright but subtle, visible but not dominating. At night, they'd be spectacular. At night, when the sun is below your horizon but still illuminating the rings from below, they would glow against the darkness. The rings would catch sunlight that Earth's shadow doesn't block, at least for part of the night. Early in the evening, after sunset, the western portion of the rings would glow brilliantly, lit by the sun that just set from your perspective. Late at night, near midnight, the rings might pass into Earth's shadow and dim significantly, visible only as a dark band blocking stars. Before dawn, the eastern portion of the rings would begin to glow again as they catch the sun that's about to rise. the amount of light reflected by the rings would be substantial. Earth's rings, if made of ice like Saturn's, would reflect about 60 to 70% of the sunlight, hitting them. During times when the rings are fully illuminated and visible in your night sky, they would provide meaningful illumination, not enough to read by, but enough to see clearly. This is light that Saturn's rings provide to Saturn's cloud tops, and it's been measured. For Earth, the effect would be similar. Nights with ring light would be noticeably brighter than nights without, especially when the moon is absent. From high northern latitudes, say 60 degrees north, the rings would appear as a lower arc across the southern sky, never rising more than 30 degrees above the horizon. But they'd be visible almost edge to face now, the disk tilted toward you, showing more structure, more detail. The variation in brightness across different parts of the rings would be clear. The Cassini division equivalent, if Earth's rings had one, would be visible as a dark line. From the Arctic Circle, 70 degrees north, the rings would hug the southern horizon, a bright arc that never rises high. From the North Pole itself, the rings would circle the entire horizon, visible in all directions at once, forming a complete thin, bright ring around the edge of the world from your perspective. You'd be looking down at the rings from above their plane. They'd surround Earth below you, and you'd see their upper surface as a circular band at the horizon, perhaps glowing in sunlight, perhaps dark in Earth's shadow depending on the time of year. The same effects would occur in the southern hemisphere, reversed. From the South Pole, you'd see the rings circling the northern horizon. From mid-southern latitudes, they'd arc across the northern sky. From the southern tropic, they'd be nearly overhead. The exact appearance would change throughout the year, not because the rings move, but because Earth's axis is tilted 23.5 degrees relative to its orbital plane. This tilt creates our seasons. It also means that the angle between Earth's equator and the Sun changes throughout the year. During the March equinox, Earth's axis points neither toward nor away from the Sun. The equator faces the Sun directly. The rings, orbiting in the equatorial plane, would be edge-on to the Sun. They'd be illuminated from the side, and their shadow would fall directly on the equator. During the June solstice, Earth's northern hemisphere tilts toward the Sun. The rings, locked in the equatorial plane, would now be tilted relative to incoming sunlight. The Sun would illuminate the northern face of the rings. Their shadow would fall across the southern hemisphere. From the northern hemisphere, you'd see the illuminated top surface of the rings, bright and detailed. From the southern hemisphere, you'd see them in silhouette against the Sun, or darkened, with only the edges catching light. During the September equinox, we'd return to edge-on illumination. During the December solstice, the southern face would be illuminated, the shadow would fall across the northern hemisphere, and southern hemisphere viewers would see the bright face of the rings, while northern viewers would see them darkened. This creates a seasonal cycle of ring visibility that would be obvious to anyone living on Earth. Half the year, your hemisphere sees the bright face. Half the year, you see the shadow side. The transition occurs gradually over weeks, the illumination angle shifting day by day, the appearance of the rings changing slowly but noticeably. People would track this. Calendars would note it. The moment when the rings shift from bright to shadowed would mark a point in the seasonal cycle just as clearly as the equinoxes mark the transition between winter and summer. The color of the rings would depend on their composition. Saturn's rings appear nearly white in true color images with subtle variations. Some regions are slightly more tan, others more blue-white. This comes from the purity of the ice and the amount of contamination from dust and organic compounds. If Earth's rings were ice, they'd likely look similar, predominantly white to pale blue, reflecting about 60 to 70% of visible light. If they were made of rockier material, similar to our Moon's composition, they'd be darker, gray to tan, reflecting only about 12% of light. The visual impact would be less dramatic with rocky rings, but they'd still be clearly visible, especially at night. From space, looking back at Earth, the rings would be one of the most striking features. Astronauts on the International Space Station would orbit below the rings, passing under them twice per orbit. Looking up at the right times, they'd see the rings stretching above them, a vast structure dwarfing Earth itself in width, though paper-thin in comparison. From the Moon, Earth would no longer be a simple blue marble. It would be a blue sphere with a bright line through it, tilted slightly, the line rotating as Earth turns, never changing position relative to Earth's equator. The view would be iconic, instantly recognizable, utterly unlike any other planet in the solar system. This is what rings would look like. Not an artist's impression or a vague description, but a specific, predictable appearance based on geometry, reflectivity, and the physics of light. Every detail described here follows from established measurements and verified principles. And now that we can picture the rings themselves, we can consider their most obvious effect: the shadow they would cast on Earth's surface. Shadows are simple. An opaque object blocks light. The region behind that object, from the light's perspective, receives no direct illumination. Planetary rings are opaque enough to cast shadows. We've seen Saturn's shadow fall across its rings countless times in Cassini images, a dark band where the planet blocks sunlight. We've also seen ring shadows fall on Saturn's clouds, dark lines that move across the planet's face as Saturn rotates. Earth's rings would cast similar shadows. The shadow would be a band, darker than the surrounding area, moving across Earth's surface as Earth rotates underneath the stationary ring system. The width, position, and intensity of this shadow would vary with season and latitude, but it would always be present during daylight hours somewhere on the planet. Let's establish the geometry carefully. The rings orbit in Earth's equatorial plane. The Sun's light comes from varying directions throughout the year because Earth's axis is tilted. During the equinoxes, when Earth's axis points perpendicular to the Sun's direction, sunlight hits the equator straight on. The rings, being in the equatorial plane, are edge-on to the Sun. At this orientation, the rings cast the narrowest possible shadow, a thin line directly on the equator. The shadow would sweep around the planet as Earth rotates, always following the equator, always narrow, perhaps a few hundred kilometers wide, depending on the vertical thickness of the rings and the slight spreading from atmospheric scattering. During the solstices, the geometry changes dramatically. At the June solstice, Earth's northern hemisphere tilts 23.5 degrees toward the Sun. The southern hemisphere tilts away by the same amount. Sunlight now hits the rings at an angle. The shadow cast by the rings falls not on the equator, but on the southern hemisphere, displaced south by an amount that depends on the height of the rings and the angle of incoming sunlight. The shadow would be wide, much wider than during the equinox. It would stretch from the inner edge of the rings to the outer edge, projected onto Earth's curved surface, creating a band that could be thousands of kilometers wide at its peak. This shadow band would still sweep around the planet as Earth rotates, but now it would travel through the southern hemisphere, crossing regions that might be experiencing their local winter at that time, at the December solstice. The situation reverses. The southern hemisphere tilts toward the Sun, the northern hemisphere away, and the ring shadow falls across the northern hemisphere instead. Again, thousands of kilometers wide, rotating around the planet, darker than the surrounding areas, noticeably cooler. The intensity of the shadow would not be absolute darkness. Some light would scatter into the shadowed region from the surrounding atmosphere. Near the edges of the shadow, the transition would be gradual, not sharp. But in the center of the shadow, the reduction in direct sunlight would be significant. Estimates based on Saturn's ring opacity suggest that 70 to 90% of direct sunlight would be blocked in the densest parts of the shadow. Not total darkness, but something like heavy cloud cover on an overcast day. Except the sky above would still be blue and stars would not be visible. The sun would be partially or completely obscured by the rings from certain positions within the shadow. This would have climate effects. They wouldn't be catastrophic, but they would be measurable. Regions that spend significant portions of the year in ring shadow would be cooler than regions at similar latitude without shadow coverage. The cooling would be modest, a few degrees Celsius on average, but persistent. Over thousands of years, this could influence vegetation patterns, animal migration, ocean currents, and atmospheric circulation. The shadow's width and position would change throughout the year, creating a seasonal pattern more complex than Earth's existing seasonal cycle. Currently, seasons are driven primarily by the angle of sunlight and the length of daylight hours, both caused by Earth's axial tilt. With rings, you'd add a third factor: shadow coverage. Some latitudes would experience ring shadow during their winter, compounding the cold. Others would experience shadow during summer, moderating the heat. The exact pattern would depend on latitude and the timing of the solstices relative to Earth's position in its orbit. At the equator, the shadow would pass through twice per day during the equinoxes, once as it sweeps around in the morning and again in the evening, creating two brief periods of partial dimming. During the solstices, the equator would largely escape the shadow, which would be displaced north or south. Mid-latitudes in the summer hemisphere would avoid the shadow entirely. Mid-latitudes in the winter hemisphere would experience the shadow daily, a regular dimming lasting several hours as the shadow band swept past during local daylight. High latitudes in the winter hemisphere might spend entire days in partial ring shadow during the weeks around the solstice. The shadow would merge with the already weak winter sunlight, creating conditions darker than they would be otherwise. In extreme cases, near the Arctic or Antarctic circles during their respective winters, the combination of low sun angle and ring shadow could create twilight conditions at what would normally be midday. But this isn't apocalyptic. It's not an eternal winter. It's a localized, seasonal dimming that would be significant but not world-ending. Comparable, perhaps, to the difference between living under frequent cloud cover versus living in a desert with constant sun. Life would adapt. Plants would adjust their growing seasons. Animals would time their migrations and breeding cycles to account for the light patterns. Human civilizations, if they developed under these conditions, would build their agricultural calendars around the shadow cycle, just as we currently build them around the regular seasons. The shadow would also be beautiful in its own way. If you were standing at a location about to enter the ring shadow, you'd see it approaching. The sky wouldn't darken suddenly. You'd see a distinct band of deeper blue moving across the landscape, shading the distant hills or forests or buildings. The light would gradually dim, becoming softer, more diffused. Then the shadow would pass over you. The temperature would drop slightly. The quality of light would change, becoming more like late afternoon even if it was only noon. And then, depending on your latitude and the season, the shadow would continue moving, passing beyond you, or it might persist for hours before Earth's rotation carried you out of it. At night, the shadow would be invisible, obviously. You can't cast a visible shadow without light to block, but the effect of the shadow would still be present in the data, in the temperature records, in the patterns of plant growth and animal behavior. The shadow would be a constant, predictable feature of Earth's environment, as reliable as the sunrise, as regular as the tides. Speaking of tides, the rings themselves would interact with Earth's gravitational field and with the Moon in ways that would create subtle but real effects on both the rings and on Earth. Let's explore those gravitational interactions. Next, gravity doesn't just hold the rings in orbit, it shapes them. It influences their structure, their density distribution, and their long-term stability. And the rings, in turn, exert their own gravitational influence, though it's small compared to Earth's mass. Each particle in the rings is in its own orbit, traveling at the precise speed needed to balance Earth's gravitational pull at that altitude with the centrifugal force of its circular motion. Particles closer to Earth orbit faster. Particles farther out orbit slower. This creates differential motion within the ring system. Particles at the inner edge might complete an orbit in about 3 hours. Particles at the outer edge might take 25 hours or more. This difference in orbital speed is why rings spread out into thin disks rather than remaining clumped together. If two particles at slightly different altitudes were to drift toward each other, their different orbital speeds would cause them to collide, gently. These collisions don't shatter the particles, usually. They're low-velocity encounters, a few meters per second at most. The particles might chip small fragments off each other. They might stick together if they're icy and conditions are right. Most likely, they bounce apart and continue in slightly modified orbits. Over millions of years, countless billions of these gentle collisions grind the particles down, creating a distribution of sizes from house-sized boulders to microscopic dust. The collisions also dissipate energy. Kinetic energy converts to heat during inelastic collisions. This gradual energy loss causes the ring system to flatten over time, becoming thinner and thinner until the vertical thickness is minimal compared to the horizontal extent. Saturn's rings are the flattest known structures in the solar system relative to their size. Some regions are only 10 meters thick, despite stretching hundreds of thousands of kilometers wide. Earth's rings would likely achieve similar flatness given enough time. Gravity creates other structures in the rings as well. The Moon's gravitational influence would create waves and spiral density patterns. As the Moon orbits Earth every 27.3 days, its gravity would pull on the ring particles, creating regions of slightly higher and lower density. These wouldn't be stable structures. They'd move and evolve like waves in water, propagating through the ring system at speeds determined by the mass distribution and orbital mechanics. In some cases, gravitational resonances could create gaps. If a region of the rings has an orbital period that's a simple fraction of the Moon's orbital period, such as 1/2 or 1/3, particles in that region would experience regular periodic tugs from the Moon, always at the same point in their orbit. Over many orbits, these regular tugs would push particles out of that region, creating a gap. Saturn has many such gaps, cleared by resonances with its various moons. Earth, with only one large moon, would have fewer resonance gaps, but they would likely exist. The rings themselves have mass, though not much compared to Earth. If we assume Earth's rings contain roughly as much material as Saturn's rings, proportional to the planet's size, we might have somewhere around 10 to the power of 19 kilograms of ring material. That's about 1/10,000,000th of Earth's mass. It's significant compared to, say, a mountain or even a large asteroid, but it's negligible compared to a planet. This small mass means the rings wouldn't significantly affect Earth's orbit, rotation, or tidal patterns. Earth's tides are dominated by the Moon's gravity, with a smaller contribution from the Sun. The rings, spread out in a thin disk, would contribute essentially nothing to tidal forces on Earth's oceans or crust. You wouldn't notice any difference in ocean tides because of the rings. However, the rings would feel tidal forces from Earth. Earth's gravity creates a gradient across the width of the ring system. The inner edge is pulled more strongly than the outer edge. This tidal force is actually what confines the rings to a thin disk. Particles that drift too far up or down from the equatorial plane experience a restoring force pulling them back toward the plane. It's the same tidal force that would tear apart a moon that ventures inside the Roche limit. For ring particles, it maintains the flat structure. Tidal forces also cause the rings to spread slowly over time. Collisions between particles redistribute angular momentum. Some particles lose angular momentum and drift inward. Others gain angular momentum and drift outward. Over millions of years, this process causes rings to slowly expand and eventually rain down onto the planet or escape into space. Saturn's rings are believed to be doing this. They may be relatively young, perhaps only a few 100 million years old, and they may disappear in another few 100 million years as the material gradually disperses. Earth's rings would follow the same pattern. They wouldn't be permanent on geological timescales. Given sufficient time, they would fade, the particles either falling into Earth's atmosphere and burning up, or drifting outward and escaping. The exact lifetime would depend on the mass and distribution of the ring material, but estimates for ice rings around a planet like Earth suggest lifetimes of tens to hundreds of millions of years. During their existence, the rings would be dynamically active. Particles would collide constantly. Moonlets, small, temporary agglomerations of particles, might form and break apart. Electromagnetic forces from Earth's magnetosphere would charge some particles and alter their orbits slightly. Radiation pressure from the Sun would push smaller particles outward, creating a subtle size segregation with the smallest dust at the outer edges. All of these effects are observed in Saturn's rings. All are consequences of well-understood physics. All would occur in Earth's rings if they existed. The rings would not be a static decoration in the sky. They would be a living system, evolving, changing, responding to forces both gravitational and non-gravitational, maintained in a kind of dynamic equilibrium between the various processes pushing the particles around and the overall structure imposed by Earth's gravity and rotation. One effect worth noting specifically is orbital resonances with objects other than the Moon. Earth has many artificial satellites. If Earth had rings and humanity still developed space technology, some of those satellites would orbit within or near the rings. Their gravitational influence would be tiny compared to the Moon, but for satellites in resonant orbits, even tiny forces repeated over and over can create structure. We might see very faint gaps or density waves caused by GPS satellites, weather satellites, or other orbital infrastructure. The rings and humanity's use of space would be intimately linked, each affecting the other in small but cumulative ways. But let's return to the view from the ground, and specifically, let's consider what the night sky would look like with rings present. Because the most dramatic visual impact of Earth's rings wouldn't be during the day. It would be at night, when the rings catch sunlight that the ground doesn't receive and glow against the darkness. On a clear night far from city lights, you can see about 2,500 stars with the naked eye. The Milky Way stretches across the sky as a diffuse band of light, the combined glow of billions of distant stars. Planets shine steadily, brighter than most stars. The Moon, when it's up, dominates everything, casting shadows and washing out faint stars with scattered light. This is Earth's night sky as it exists. Add rings and everything changes. First, the rings themselves become the dominant feature whenever they're illuminated. For half the year in each hemisphere, the rings would be lit by the sun during nighttime hours. Not all night, but for significant portions of it. Here's why. The rings orbit at altitudes between roughly 9,000 and 80,000 kilometers. Earth's shadow, the cone of darkness trailing behind Earth opposite the sun, extends about 1.4 million kilometers into space. The rings pass through this shadow, but not always completely. Depending on the season and the time of night, parts of the rings can be illuminated by sunlight even when the ground is in darkness. At the equinoxes, when the sun's light hits Earth's equator straight on, the rings are edge-on to the sun. Earth's shadow, at the altitude of the rings, is almost the same diameter as Earth itself, about 12,700 kilometers. The rings extend much farther than this horizontally. The portions of the rings far from Earth, stretched out to the sides, remain in sunlight even at midnight. From the ground, looking up at the rings at night during the equinox, you'd see the ring band lit up at the horizons, glowing brightly near the north and south horizons depending on your latitude, but dark overhead where the rings pass through Earth's shadow. During the solstices, the geometry shifts. The rings tilt relative to the sun. Now, more of the ring can catch sunlight during the night, or alternatively, more of the ring might be shadowed depending on which hemisphere you're in and which solstice it is. In the summer hemisphere, when the sun is relatively high, even at midnight for high-latitude locations, the rings would catch that low-angle sunlight and glow brilliantly throughout much of the night. In the winter hemisphere, the rings might spend more time in Earth's shadow and be darker at night. But let's focus on a specific scenario. You're at 45 degrees north latitude. It's a few weeks after the March equinox. You go outside at 10 p.m. local time. The sun set 2 hours ago. The sky is fully dark, or as dark as it gets with rings. Looking south, you see the rings arcing across the southern sky. They reach about 45 degrees above the southern horizon at their highest point. The western part of the arc, the part closer to where the sun set, glows brilliantly. It's bright enough that you can see your shadow on the ground, a soft, diffused shadow, not sharp like a shadow from the moon or artificial lights, but definitely there. The light is pale blue-white, the color of reflected sunlight from ice. The arc is wide, several degrees, and you can see structure in it. Brighter patches, darker lanes, subtle variations in brightness. As your eyes trace the arc toward the east, it dims. The middle section, the part overhead or nearly so, passes through Earth's shadow. Here the rings are dark, visible only as a black band blocking the stars. You can see stars on either side of the ring band, but where the rings are, there's nothing. Just darkness. It's eerie in a peaceful way, this absence cutting through the sky. Continue tracing eastward. The rings emerge from Earth's shadow. The eastern part of the arc begins to glow, catching sunlight that's coming from the side, from the sun that's now far below the western horizon, but still illuminating objects high above Earth's shadow. This glow is fainter than the western glow was earlier in the evening, but it's definitely there, a gentle radiance that will grow brighter as the night progresses and the Earth continues turning, bringing the eastern rings more squarely into sunlight relative to your position. The ring light would provide real illumination, not as much as the moon, which reflects about 12% of sunlight from a solid surface at a distance of 384,000 kilometers. The rings are farther in some places, nearer in others, and they reflect more light per unit area if they're icy, but they're spread out over a huge area rather than concentrated in one disk like the moon. The total amount of light reaching Earth from the rings would be less than from a full moon, but more than from a crescent moon. Enough to see clearly, enough to walk without a flashlight, enough to reduce the visibility of faint stars. And that's the trade-off. The rings would be spectacular, but they would light pollute the night sky naturally. The glow from the rings, combined with atmospheric scattering of that glow, would create a permanent background light level higher than the natural darkness we currently experience on moonless nights in remote locations. Faint galaxies, nebulae, and dim stars would be harder to see. The Milky Way would still be visible, but it would be less prominent, washed out by ring shine just as it's currently washed out by moonlight or artificial light pollution. Astronomers would have to account for this. They'd plan observations for times when the rings are least illuminated, perhaps during new moon when the rings and moon are both near the sun and largely in Earth's shadow during nighttime hours. Or they'd build observatories in regions where the rings are least visible, perhaps high-latitude locations where the rings hug the horizon and contribute less sky glow. But for most people, the trade-off would be worth it. The sheer beauty of seeing the rings every clear night would outweigh the loss of faint, deep sky objects. Rings would become part of the cultural landscape of the night, referenced in art, literature, mythology, religion. They'd be more prominent than the moon in some ways, always present when visible, always in the same position relative to the horizon from any given location, a permanent fixture rather than a wandering light. Now add the moon to this picture. Our moon would still orbit Earth every 27.3 days, just as it does now. Its orbit is inclined about 5 degrees to Earth's equator, so it would sometimes pass in front of the rings from certain perspectives and sometimes pass behind. When the moon is full, shining brightly, the rings would be less noticeable, overpowered by the moon's brilliance. When the moon is new, absent from the night sky, the rings would dominate, providing the primary source of nighttime illumination. During a crescent moon, you'd have both. The moon hanging in the west after sunset, a thin, bright curve and the rings arcing across the sky, glowing softly, the two light sources creating a double-shadowed landscape, soft overlapping shadows cast by both moon and rings. Photographers would have a field day. The visual complexity would be stunning. Occasionally, the moon would pass directly in front of a bright section of the rings, creating what we might call a ring occultation. For a brief period, that section of the rings would disappear behind the moon, then re-emerge on the other side. This would be visible to the naked eye, a slow event taking an hour or more as the moon's orbital motion carried it across the ring's width in the sky. Ancient astronomers would track these events, using them to refine their understanding of the moon's orbit and the ring's structure. Planets would also pass behind the rings occasionally. Venus, Mars, Jupiter, Saturn, visible as bright points of light wandering through the zodiac, would sometimes move into the same region of sky as the rings. When this happens, the planet would shine through the rings if the rings are thin enough at that point, or it might be occulted, blocked temporarily. These events would be rarer, since planets move slowly and the rings occupy a fixed path across the sky, but they would occur and they would be noted. Meteors would look different too. Meteor showers occur when Earth passes through debris trails left by comets. The tiny particles hit Earth's atmosphere at high speed and burn up, creating streaks of light. With rings present, some meteors might pass behind the rings from your perspective. You'd see a meteor streak suddenly disappear as it passes behind the ring band, then reappear on the other side. Or a meteor might appear to originate from the ring itself, an illusion of perspective when the meteor's path and the ring's position in the sky happen to align. The night sky would be fundamentally different. Not worse, not better, just different. More light, less darkness, greater visual complexity, a permanent structure where currently there's only empty space occasionally occupied by the moon. It would be a sky worth staying up to watch, worth traveling to dark sites to see clearly, worth photographing and painting and describing in poetry. The rings would be as central to human experience of the night as the moon currently is, perhaps even more so because of their constancy and their sheer scale. During a lunar eclipse, when Earth's shadow falls on the moon turns dark and reddish, lit only by sunlight refracted through Earth's atmosphere. With rings present, a lunar eclipse would offer a special viewing opportunity. The moon would be dark, the rings might also be in shadow depending on the geometry, and the sky would be unusually dark for a change. This would be the best time to observe faint stars and galaxies. Ancient cultures might associate lunar eclipses with a temporary clearing of the sky, a rare gift of darkness. And then there's the question of how human history would have developed differently if rings had always been present. This is harder to address with the same rigor as the physics and visual appearance because history is contingent and unpredictable. But we can make some educated guesses based on how prominent features of the sky have historically influenced human culture. The sun and moon have shaped human culture profoundly. They've been worshipped as deities, used to structure calendars, served as symbols in mythology, and inspired countless works of art and literature. The sun's regular appearance defines the day. The moon's phases provide a natural monthly cycle. Both are unavoidable, visible to everyone, impossible to ignore. Rings would be similarly unavoidable. In some ways more so because, unlike the sun, you can look directly at rings without damaging your eyes, and unlike the moon, rings don't come and go on a monthly cycle. They're always there, or at least always there from latitudes where they're visible. This permanence would make them central to the human experience of the world. Early human societies, developing in Africa tens of thousands of years ago, would have seen the rings arcing across the sky. From equatorial Africa, the rings would appear edge-on, a bright line passing overhead. Early humans would have no concept of what rings are. They might interpret them as a bridge, a pathway, a division between sky realms. The line might represent duality, the separation of opposites, the connection between Earth and heaven. As humans migrated to different latitudes, the appearance of the rings would change. Populations moving north or south would see the rings tilt, becoming a great arc rather than a line. This might be interpreted as regional differences in the cosmic structure. Groups that traveled far enough to see the rings change significantly might develop origin myths about journeying from the land where the sky bridge is straight to the land where it curves. Civilizations that developed writing and astronomy would begin to study the rings systematically. They'd note that the rings don't move relative to the stars over the course of a night, unlike the moon and planets. They'd observe that the ring's brightness changes with the seasons. They'd track the position of the moon relative to the rings, noting occultations and conjunctions. They might discover that the rings cast shadows on Earth, observing the shadow band moving across the landscape each day during certain seasons. Some conclusions would be correct. Ancient astronomers might determine that the rings circle Earth, that they're aligned with the equator, that they're illuminated by the sun. Other conclusions might be incorrect or mixed with mythology. The rings might be seen as a physical structure, perhaps made of crystal or divine material, perhaps holding up the heavens, perhaps serving as a home for gods or spirits. Calendars might incorporate ring phenomena. The moment when the ring shadow shifts from the northern hemisphere to the southern, or vice versa, would be a precisely observable event marking the equinox. This would provide a clear, visually obvious way to track the year, potentially more obvious than tracking the sun's position relative to the stars. Agricultural societies would plant and harvest based on the ring shadow's position and the associated climate effects. Navigation would be affected. At sea or traveling across featureless terrain, the rings would provide a constant reference for direction, assuming you know what latitude you're at. From any given position, the rings point toward the equator. If you're north of the equator, the rings arc across the southern sky, and the highest point of that arc points south. This would be less precise than using the sun or pole star, but it would be available whenever the rings are visible, which is whenever the sky is clear. The cultural impact would extend to art and architecture. Structures might be aligned with the rings. Monuments might be built to frame specific views of the rings at specific times of year. Paintings and mosaics would depict the rings as a standard element of landscape and sky scenes. Literature would reference the rings constantly, using them as metaphors for permanence, for division, for the unreachable, for the divine. Religious and philosophical traditions would incorporate the rings into their cosmologies. Some traditions might see the rings as a barrier between the mortal world and the heavens. Others might see them as a sign of cosmic order, the universe's structure made visible. Some might worship the rings themselves. Others might view them as neutral natural phenomena, no more divine than mountains or oceans. Importantly, the existence of rings wouldn't prevent the eventual development of science and accurate astronomy. Ancient Greek astronomers figured out that the Earth is round, calculated its circumference, and determined the distances to the Moon and Sun using geometry and observation, all without telescopes. Given similar observations of the rings, their apparent position and brightness, how they're illuminated by the sun, eventually someone would propose that the rings are material objects orbiting Earth, held in place by the same force that keeps the Moon in orbit and causes objects to fall. This might happen earlier than the development of similar theories did in our history, because the rings provide such an obvious example of orbital mechanics. They orbit Earth visibly, even though the individual particle's motion is too small to see. They're clearly subject to the same sun that lights the daytime sky. They're clearly not gods or spirits, but physical phenomena. This might accelerate the development of physics and astronomy, or it might not. History doesn't follow simple cause and effect in these matters. In the modern era, with telescopes and space travel, the rings would be studied exhaustively. Telescopes would reveal the ring structure in detail, showing the gaps, the divisions, the variation in brightness and color. Spectroscopes would determine composition. Eventually, space probes would visit the rings, fly through them, collect samples. Astronauts would see the rings from above and below, passing through the ring plane on missions to higher orbits. The rings would be both an obstacle and a resource for space activities. But that's a topic substantial enough to deserve its own section, so let's turn to that now. Launching from Earth to space requires reaching orbital velocity, approximately 7.8 kilometers per second for low Earth orbit. This speed is necessary to balance gravitational pull with the centrifugal force of circular motion. Achieving this speed requires powerful rockets, significant fuel, and careful trajectory planning. None of this would change if Earth had rings. The fundamental physics of reaching orbit remains the same. But the rings would add complications. They occupy the space between approximately 9,000 kilometers altitude and 80,000 kilometers altitude. Many satellites orbit within this range or pass through it to reach higher orbits. With rings present, every launch, orbit adjustment, and re-entry would need to account for the presence of billions of ring particles, each one a potential collision hazard. Ring particles orbit at specific speeds determined by their altitude. At 9,000 kilometers, orbital velocity is about 4.5 kilometers per second. At 80,000 kilometers, it's about 2.2 kilometers per second. A satellite traveling through the rings at a different inclination would hit particles at relative velocities of several kilometers per second. At these speeds, even a small particle carries enormous kinetic energy. A piece of ice the size of a marble, 1 centimeter in diameter, hitting a spacecraft at 5 kilometers per second would impact with energy equivalent to several kilograms of TNT. It would destroy the spacecraft. This means that satellites couldn't orbit randomly through the rings. They'd need to orbit in the same plane as the rings, the equatorial plane, and match the ring particles' orbital velocity. This essentially means satellites would need to orbit within the rings, moving with them, not through them. Collisions would still occur, but they'd be low-velocity encounters, bumps rather than catastrophic impacts. Alternatively, satellites could orbit outside the ring system entirely, either much closer to Earth than 9,000 kilometers or much farther than 80,000 kilometers. Low Earth orbit, where the International Space Station orbits at 410 kilometers, would be safe. Geostationary orbit at 35,786 kilometers would be impossible, since that's within the ring system. Communication satellites would need to orbit higher or lower. Reaching the moon or traveling to other planets would require passing through the rings. Spacecraft would need shielding. They'd need to calculate the safest trajectory, perhaps passing through a gap in the rings where particle density is lowest. Or they'd accept the risk and armor the spacecraft heavily, knowing that some impacts are inevitable, but hoping they won't hit anything large enough to cause critical damage. Space agencies would map the ring structure carefully. They'd identify regions of higher and lower density. They'd track larger particles, the boulders and moonlets that pose the greatest danger, and calculate their orbits precisely to avoid them. Over time, humanity would develop techniques for safely navigating the rings, just as we've developed techniques for avoiding space debris in near-Earth orbit today. The rings would also be a resource. Ice is valuable in space. Water can be split into hydrogen and oxygen, providing rocket fuel and breathing air. It's also useful for radiation shielding, and obviously for drinking and growing food. The rings contain enormous quantities of ice, easily accessible from Earth orbit. Mining operations could be established to collect ring material, process it, and supply water to orbital stations and spacecraft. Such mining would be tricky. You can't just fly into the rings and scoop up material without matching velocity. But once you're orbiting within the rings, moving at the same speed as the particles, you could deploy collection devices. Nets, electromagnetic traps, or simple mechanical scoops could gather particles as they drift by. The collected material would then need to be transported to wherever it's needed, perhaps melted and stored in tanks, or transported as ice if refrigeration is available. Over time, mining might deplete certain regions of the rings, creating artificial gaps or thinning the density. This would actually be helpful for space navigation, creating safe corridors through the ring system. But it would also change the appearance of the rings from Earth, potentially dimming them or altering their structure. Humanity would need to decide whether the practical benefits of ring mining outweigh the aesthetic and cultural value of keeping the rings intact. Scientific research would benefit enormously from having rings. They'd be a natural laboratory for studying orbital mechanics, collisional processes, and the behavior of vast numbers of particles under gravity. Lessons learned from studying Earth's rings would apply to understanding Saturn's rings, asteroid belts, protoplanetary disks, and other cosmic structures made of orbiting particles. Instruments on satellites orbiting within the rings could measure particle size distribution directly, sample composition, study electromagnetic effects, and observe close-up the processes that create ring structure. This would be far more detailed than observations of Saturn's rings from remote spacecraft. Earth's rings would be accessible, touchable, right on our doorstep. Tourism would be inevitable. Once space travel becomes routine, people would pay to see the rings up close. Hotels or stations might be built orbiting within the rings, offering views both outward toward the rings themselves and downward toward Earth, with the rings spread below. Imagine looking out a window and seeing countless icy particles drifting past, each one catching sunlight, the swarm extending in all directions, and beyond them Earth, blue and white, partially shadowed by the rings themselves. The rings would also pose a long-term threat to spacecraft from debris accumulation. Currently, space debris in near-Earth orbit is a growing problem. Old satellites, spent rocket stages, and fragments from collisions create a cloud of junk that poses collision risks. With rings present, any debris created in or near the ring region would become part of the ring system, adding to the particle population. Over time, this could make the rings more hazardous, increasing collision probability and creating a runaway cascade where collisions create more debris, which causes more collisions. This is known as the Kessler syndrome, and it's a serious concern for Earth's orbital environment even without rings. With rings, the problem would be worse because the ring system provides a natural sink for debris. Anything orbiting near the ring plane would eventually interact with ring particles through collisions or gravitational perturbations, potentially being captured into the ring system rather than decaying into the atmosphere or escaping to higher orbits. Space agencies would need strict regulations. No spacecraft could be abandoned in the ring region. Everything launched through the rings would need to be either retrieved, deorbited into Earth's atmosphere, or boosted to a disposal orbit outside the ring system. This would add cost and complexity to every mission, but it would be necessary to preserve the long-term usability of near-Earth space. Despite these challenges, humanity would adapt. We'd learn to work within the constraints the rings impose. We'd develop technologies and procedures to make space travel safe and routine, even with rings present. And we'd benefit from the resources the rings provide, the scientific opportunities they offer, and yes, the sheer inspiration of having such a structure visible from the ground, a constant reminder that Earth is part of a larger cosmic environment. All of this is based on how we currently deal with orbital debris, how we plan missions to avoid collisions, and how we've proposed using space resources in the future. The rings would amplify existing challenges and opportunities without introducing fundamentally new physics or impossible obstacles. But we're assuming the rings are stable, that they persist long enough for these scenarios to play out. Let's examine that assumption more carefully by looking at how long rings last and what causes them to eventually disappear. Nothing lasts forever. Mountains erode, oceans evaporate, stars burn out. Planetary rings are no exception. They're temporary structures on cosmic timescales, maintained by a balance of forces that gradually shifts until the rings spread out and disappear. The primary mechanism for ring decay is the redistribution of angular momentum through collisions. When two ring particles collide, they exchange momentum. On average, over billions of collisions, this causes some particles to lose angular momentum and drift inward toward the planet, while other particles gain angular momentum and drift outward. The process is slow but relentless. Particles that drift inward eventually reach Earth's upper atmosphere. At altitudes below about 200 kilometers, atmospheric drag becomes significant. The thin wisps of air at these altitudes, mostly hydrogen and helium with traces of oxygen and nitrogen, create friction against objects moving at orbital velocity. This friction removes energy, causing orbits to decay further, creating a runaway process where the particle spirals inward faster and faster until it enters the dense atmosphere and burns up like a meteor. For Earth's rings, particles wouldn't need to drift all the way down to 200 kilometers. They just need to drift inward from the ring region, crossing the Roche limit boundary, and continuing down through thousands of kilometers of empty space until atmospheric drag catches them. The time required for this process depends on the collision rate, the mass of the particles, and the initial distribution of angular momentum in the ring system. Studies of Saturn's rings suggest that they lose material continuously. Measurements from the Cassini spacecraft detected rain of ring material falling into Saturn's atmosphere, a steady drizzle of charged ice particles pulled downward by gravity and dragged along by Saturn's magnetic field. The amount of material falling is small compared to the total mass of the rings, but over millions of years it adds up. Current estimates suggest Saturn's rings might have only tens to hundreds of millions of years left before they vanish completely. Earth's rings would face similar decay rates. The exact numbers would depend on the ring composition, structure, and the strength of Earth's magnetic field, but the principle is the same. Rings are doomed. They form, they persist for a geologically brief period, and then they fade away, raining down onto the planet that created them. This means that if Earth had rings today, they would be relatively young on geological timescales. Earth is 4.54 billion years old. If rings lasted only a few 100 million years maximum, then Earth's current rings would have formed sometime in the past few 100 million years, likely from the breakup of a captured asteroid or moon, or possibly from a massive impact event that sent debris into orbit. The youth of the rings would have implications for paleoclimate. If the rings cast significant shadows on Earth's surface, and those shadows affected climate, then the formation of the rings would correspond to a shift in climate patterns. Geologists studying ancient climates might see evidence of this in sediment cores, ice cores, or fossil records. A sudden cooling in certain latitude bands a few 100 million years ago, without a corresponding change in Earth's orbit or solar output, might be explained by the formation of ring shadows. Conversely, if Earth had rings in the distant past but no longer does, their disappearance would leave traces. Ancient human civilizations, if they arose while Earth still had faint remnants of rings, might have recorded them in their oldest myths and astronomical observations. The gradual fading of the rings over thousands of years would be noticeable over many human generations. Stories might speak of a time when the sky bridge was brighter, or when the path of the gods was more clearly visible, and modern historians might interpret these as cultural memories of actual ring decay. But we're assuming here that Earth's rings are made of ice or rock, stable materials that don't actively evaporate or degrade beyond collisional grinding. Some ring systems might include volatile materials, substances that sublimate over time when exposed to sunlight. If Earth's rings contained dry ice, frozen carbon dioxide, or frozen nitrogen, these substances would gradually turn directly from solid to gas when illuminated by the sun, creating a slow evaporation process, independent of collisions. Saturn's rings are predominantly water ice, which sublimates extremely slowly at Saturn's distance from the Sun. Water ice is stable enough to persist for millions of years in the cold vacuum of space at Saturn's orbital radius. Earth is closer to the Sun, receiving more solar radiation, but water ice would still be relatively stable at the altitudes where rings orbit. The temperatures in Earth's ring region would be cold, perhaps -40 to -60 degrees Celsius in the shadow, and varying when illuminated, but not warm enough to rapidly evaporate ice. Some sublimation would occur, especially for smaller particles with high surface area to volume ratios, but it wouldn't be the dominant decay mechanism. More significant would be the erosion from micrometeorite impacts. Earth's rings would sit in the path of interplanetary dust, tiny particles from comets and asteroids that constantly rain down on Earth. These micrometeors, traveling at speeds of tens of kilometers per second, would strike ring particles regularly, chipping away tiny amounts of material with each impact. Over millions of years, this sandblasting effect would gradually wear down ring particles, creating dust that would then be subject to different forces than larger particles. Dust behaves differently in space than larger objects. Particles smaller than a few micrometers are significantly affected by radiation pressure from the sun. Sunlight carries momentum, and when photons strike a dust grain, they push it slightly. For very small particles, this radiation pressure can overcome gravitational attraction to the planet, causing the dust to spiral outward and eventually escape the ring system entirely. This creates a size-dependent separation in the rings, with dust continuously being removed from the system while larger particles remain. Earth's magnetic field would also play a role. Charged particles in the rings, particularly small dust grains that pick up static electrical charges, would interact with Earth's magnetosphere. The magnetic field lines guide charged particles, forcing them to spiral along the field. This can cause charged ring particles to drift in ways they wouldn't under gravity alone, potentially moving them out of the equatorial plane or altering their orbits. The exact effects depend on the strength and structure of Earth's magnetic field in the ring region, which is complex and not perfectly understood even for our current magnetosphere. All of these processes work together to gradually disassemble a ring system. Collisions redistribute angular momentum. Atmospheric drag removes inward drifting particles. Radiation pressure removes dust. Micrometeorite erosion creates more dust. Gravitational perturbations from the Moon clear resonance gaps. Electromagnetic forces shuffle charged particles around. The result is a system in constant flux, slowly losing material, gradually changing structure, maintained only temporarily before the inevitable decay. The time scale for complete ring decay would depend on many factors. A massive, dense ring system might last several 100 million years. A thinner, less massive system might disappear in tens of millions of years. The presence of shepherd moons, small moons orbiting near the rings whose gravity helps confine the ring material, could extend ring lifetimes significantly. Saturn's ring system has several shepherd moons that help maintain sharp ring edges and prevent rapid spreading. Earth, with only one large moon far outside the ring region, would lack this stabilizing influence, potentially shortening ring lifespan. But even as the rings decay, they would remain beautiful. A fading ring system would grow more diffuse, less bright, but it would still catch sunlight and glow in the night. The structure would become less sharp, gaps would widen, bright regions would dim. Ancient observers with records spanning centuries would notice the changes. Astronomers would debate whether the rings are eternal or temporary. Eventually, scientific measurement would confirm that the rings are fading, which would raise questions about their origin and whether new rings might form in the future. Could new rings form? Possibly. If another moon or large asteroid were captured by Earth's gravity and placed on a collision course, or if Earth's gravity gradually pulled a passing object inward over millions of years, that object might eventually cross the Roche limit and shatter, creating a new ring system. This is thought to happen occasionally around other planets. Jupiter, for instance, has a faint ring system that's likely replenished by material from its small inner moons, which are constantly being sandblasted by meteorite impacts that kick up dust into orbit. Earth could theoretically capture new moons. It's rare, but not impossible. An asteroid passing close enough, at just the right velocity and angle, could be captured into orbit around Earth. Over time, tidal forces might slowly pull that moon inward. Millions of years later, it would cross the Roche limit and break apart, seeding a new ring system. This cycle could repeat multiple times over Earth's history, creating rings, letting them fade, creating new ones, over and over on timescales of hundreds of millions of years. But for any given ring system, the lifetime is limited, and that makes them precious. If Earth had rings, we would be living during a special time, a window of a few 100 million years at most, when our planet happens to have this remarkable feature. Billions of years in the past, Earth might have been ringless. Billions of years in the future, Earth will almost certainly be ringless again. But now, in this moment, there would be rings, and that makes the present cosmically significant. This temporality would add depth to the cultural meaning of the rings. They're not eternal fixtures. They're transient, like ourselves, like civilizations, like species. Everything that exists now will eventually fade. The rings would be a reminder of that, visible every night, beautiful because they're temporary, precious because they won't last. And in the time they do last, they would be dynamic, evolving, responding to forces both external and internal. Watching the rings over a human lifetime, you wouldn't see them change. But watching them over geological time, comparing their appearance across millions of years through the fossil record or future evidence, you'd see a story of creation and destruction, order and entropy, stability and change, playing out in the sky above us. Let's shift now from the long-term evolution of the rings to something more immediate and human. Let's consider what it would feel like to live under these rings, not as an abstract observer, but as a person going about daily life, looking up occasionally, seeing this permanent feature of the sky, and letting it become part of the background of existence. Imagine growing up in a world where rings have always been there. You're born, you open your eyes, and eventually you see the sky. And in that sky, there's the sun during the day, maybe clouds, maybe blue emptiness, and there's the ring band cutting across, always in the same position relative to the horizon from your home, always the same width, changing only in brightness and shadow as the seasons progress. You don't think it's strange. This is just what the sky looks like. Everyone you know sees the same thing. Pictures in books show the rings. Maps of the world show the ring band stretching across the sky in different positions depending on latitude. It's as normal as having a moon, as ordinary as seeing mountains on the horizon if you live near mountains, or seeing the ocean if you live near the coast. But it's also special, and you know it's special because adults tell you about it. Teachers explain what rings are, how they work, why they're there. You learn that other planets have rings too, that Saturn's rings are even more magnificent than Earth's, that rings are structures of ice and rock held in orbit by gravity. You learn about the shadow the rings cast, how it affects climate and seasons. You learn to predict when the rings will be brightest, when they'll be darkest, when the moon will pass in front of them. As a child, you might lie in the grass on summer evenings, watching the rings glow softly against the darkening sky, trying to see structure in them, looking for the variations in brightness, making up games where the rings are bridges or roads or rivers in the sky. You might draw pictures of the rings, trying to capture their arc, their width, the way they fade near the horizons. As you grow older, the rings remain constant, but your understanding of them deepens. You learn the physics behind them. You understand that each bright point in the rings is technically millions of separate particles, that the seeming solidity is an illusion of scale, that the rings are more like a cloud than a structure. You learn about the particles' orbits, how they collide, how the system maintains itself temporarily before eventual decay. The rings become more real and somehow more beautiful because of that knowledge. When you travel, you see the rings from different latitudes. If you grew up near the equator, traveling north or south shows you the rings at different angles, arcing higher or lower in the sky, changing their relationship to the horizon. If you grew up at mid-latitudes, traveling toward the equator makes the rings rise higher, approaching the zenith, while traveling toward the poles makes them sink lower, hugging the horizon. Every location has its own ring view, its own perspective on this global feature. You might have favorite ring views, maybe the view from a particular hilltop near your home, where the rings arc perfectly over a valley. Maybe the view from a beach, where the rings reflect in the water at sunset, creating a double image. Maybe the view from a desert, where the air is so clear that you can see fine structure in the rings that's invisible from more humid climates. These personal connections to the rings would be as meaningful as any other landscape feature you love. At night, when the rings glow, you'd use them for practical purposes. Walking home from a friend's house, you'd navigate partly by ring light, which always indicates the direction of the equator. You'd know that when the rings are bright, you don't need a flashlight. You'd plan outdoor activities for nights when the rings are illuminated, knowing you'll have enough light to see clearly. Seasonal changes in the rings would mark the passing of time as clearly as changes in weather or the lengths of days. You'd notice when the ring shadow starts to shift in spring, when the rings darken in your hemisphere as winter approaches, when they brighten again in summer. These changes would feel significant, tied to agricultural cycles, to cultural festivals, to personal memories. You'd remember winters by how dark the rings were, summers by their brightness. The rings would feature in your culture's art and literature constantly. Poems about the rings, paintings depicting them, songs referencing them, stories using them as metaphors. The rings might symbolize different things in different traditions. Constancy and reliability, since they never move. Transience and impermanence, since they're known to be temporary. Division and separation, since they cut the sky in half. Unity and connection, since they circle the entire world. The meanings would be as varied as human interpretation allows. Architecture might respond to the rings. Buildings could be oriented to frame specific views of the rings through windows or doorways at certain times of day or year. Temples or monuments could align with the ring band, creating a visual connection between earthly structures and celestial ones. Cities might develop distinctive skylines that interact visually with the rings, towers, and spires that seem to touch the ring band when viewed from certain angles. Holidays and celebrations would likely be tied to ring phenomena. The days when the ring shadow shifts hemispheres, marking the equinoxes, would be major festivals. The periods when the rings are darkest or brightest might have cultural significance. Lunar occultations of the rings, when the moon passes in front of a bright section, might be considered auspicious or ominous depending on tradition. Personal milestones might be marked by the ring's appearance. Couples might get married under a bright ring-lit sky. Children born during certain ring configurations might be said to have particular qualities. Travelers might time their journeys to coincide with favorable ring illumination for easier nighttime travel. The rings would be woven into the fabric of daily life in countless small ways. Photographers would have an endless subject. The rings would appear different every day depending on weather, lighting, season, and time. Capturing the perfect ring photograph would be a lifelong pursuit for some. Time-lapse videos would show the moon moving across the ring band, or show the ring shadow crossing the landscape, or show the transition from day to night as the rings shift from daytime visibility to nighttime glow. Artists working in other media would also be inspired. Sculptors might create pieces that echo the ring's curves. Musicians might compose works that try to capture the feeling of ring-lit nights. Writers would set stories against the backdrop of the rings, using them to establish mood, mark time, or symbolize themes. The rings would be as influential artistically as any major landscape feature, perhaps more so because of their visibility and their cosmic nature. Scientists would be endlessly fascinated. Every generation would produce new studies of the rings, using increasingly sophisticated instruments to measure their composition, structure, and dynamics. Debates would continue about the rings' origin, their age, their future evolution. New discoveries would be made regularly, surprising even experts who've studied the rings for decades. The rings would provide employment for astronomers, physicists, and planetary scientists. A built-in research subject that's always accessible, always yielding new data. But for most people, most of the time, the rings would simply be there. A familiar part of the sky, glanced at occasionally, appreciated aesthetically, understood intellectually, but mostly just background. Like how we treat the moon currently, or the stars, or clouds. We know they're remarkable, we can appreciate them when we pause to think about it, but usually we're too busy with immediate concerns to spend much time contemplating them. And that's fine. That's how humans relate to their environment. The extraordinary becomes ordinary through familiarity. The ring would be extraordinary to visitors from other planets, or to people who'd never seen them before. But for those who live under them every day, they'd be home. They'd be normal. They'd be comfort and familiarity and constancy, the thing that tells you you're home when you return from a journey. The feature that's always there, reliable, unchanging on human timescales, a permanent piece of the world as you know it. Until perhaps they fade. If you lived during the final centuries or millennia of the ring's existence, you might witness their dimming, their gradual disappearance. This would be profoundly sad for a society that had always known rings. Stories would be told about how bright they used to be. Old photographs would be treasured, showing the rings in their full glory. People would make pilgrimages to dark sky locations to see the fading rings one last time. Artists would create memorial works, capturing the rings before they vanish completely. And then, one generation, the rings would be gone, and the sky would be empty in a way it hadn't been for millions of years. Or perhaps the rings would persist long enough that humanity expands beyond Earth, building colonies on the Moon, Mars, asteroids, eventually other star systems. Those colonists would look back at Earth and see the rings, a unique identifier, the ringed planet, our home. Earth would be the ringed world, the only ringed terrestrial planet anyone knows of. Special because of this feature, recognizable across the solar system and beyond. But we're speculating now about distant futures and alternative histories. Let's return to the immediate, to the concrete, to what would actually be different about Earth if rings were present. We've covered the view from the ground, the shadow effects, the orbital mechanics, the cultural implications. Let's now consider a different angle. How the existence of rings would change our scientific understanding of our place in the solar system and the universe. Earth is, as far as we know, the only planet that hosts life. It's the only world where complex chemistry has resulted in self-replicating systems that evolved into the vast diversity of organisms we see today. This makes Earth special, perhaps unique in the entire universe, though we don't know for certain. What we do know is that among the planets in our solar system, Earth is the only one with oceans of liquid water, stable surface temperatures suitable for organic chemistry, and an atmosphere rich in oxygen produced by biological processes. Rings wouldn't change any of that. Earth with rings would still be habitable, still home to life, still the unique blue world among rocky neighbors and gas giants. But rings would add another layer to Earth's distinctiveness, making it not just the living planet, but the ringed living planet, a combination that's not seen anywhere else in the solar system, and, based on our current understanding, probably quite rare in the universe as, well, ringed planets are common in our solar system. All 4 gas giants have rings. Jupiter's are faint, dusty structures fed by its small inner moons. Saturn's are massive, bright, and iconic. Uranus and Neptune both have narrow, dark ring systems made of dust and rock. But all of these are gas giants, worlds without solid surfaces, places where life as we know it couldn't exist. There are no ringed terrestrial planets in our solar system except, in this thought experiment, Earth. This would have philosophical implications. It would reinforce the idea that Earth is special not just biologically, but also physically. We'd be the only world combining solid ground, liquid water, breathable atmosphere, complex life, and orbital rings. The combination would seem almost too fortuitous, as if Earth were designed to be maximally interesting, though of course it wouldn't be design, but simply the outcome of particular historical accidents. Comparatively studying Earth's rings and the gas giants' rings would teach us about planetary formation. Ring systems are thought to be common during planetary formation, arising from the debris left over after planets coalesce from the protoplanetary disk. Most terrestrial planets lose their rings quickly, within a few million years, as the material either falls into the planet, is ejected from the system, or accretes into moons. Gas giants can retain rings longer because they're more massive, their Roche limits are farther out, and they have complex systems of moons that help stabilize ring structure. If Earth had rings, it would suggest that something unusual happened in Earth's history to create or maintain them. Perhaps a large moon was captured relatively recently, in the past few 100 million years, and then destroyed. Perhaps a massive asteroid impact sent debris into orbit that coalesced into rings rather than forming a new moon. Perhaps ancient rings have been maintained longer than expected through some stabilizing mechanism we don't fully understand. Any of these scenarios would tell us something about planetary dynamics and the evolution of terrestrial planets. Rings would also affect how we search for life on other planets. When we look for potentially habitable exoplanets around other stars, we look for certain signatures: the right size, the right distance from the star, the presence of water vapor or oxygen in the atmosphere. We currently don't look for rings because rings aren't necessary for habitability, and because detecting rings on distant planets is extremely difficult with current technology. But if Earth had rings and life, that would establish that ringed terrestrial planets can definitely host life. It wouldn't mean rings make life more likely, but it would mean we shouldn't exclude ringed planets from our search. More importantly, it would give us another data point about the variety of planetary environments where life can arise and evolve. Life on Earth has survived mass, extinctions, climate changes, asteroid impacts, and continental drift. If it also survived the formation of rings, the shadows they cast, and the changes they brought to climate and tides, that would demonstrate life's resilience even more clearly. From a cosmic perspective, rings are ephemeral. Stars last billions of years. Planets last billions of years. Moons can last billions of years if they're in stable orbits. But rings last only millions of years, a brief moment in cosmic time. For Earth to have rings at the exact moment when intelligent life has evolved and developed the ability to study them would be either a remarkable coincidence or would suggest that rings are more common in terrestrial planets' histories than we currently think. If rings are common, if most terrestrial planets go through ringed phases multiple times during their lifetimes, then observing Earth with rings would simply mean we're in one of those phases. The probability of intelligent life arising during a ringed phase becomes reasonable if ringed phases last hundreds of millions of years and occur multiple times throughout a planet's multi-billion-year history. Human civilization has existed for maybe 10,000 years. Anatomically modern humans for a few 100,000 years. Complex life on Earth has existed for over 500 million years. If Earth had rings that formed 200 million years ago and will last another 200 million years, then nearly half of the time complex life has existed on Earth would overlap with the existence of rings. This would make rings a feature of Earth's environment that life evolved with and adapted to, not something alien or new. The shadow patterns would have influenced the evolution of plants, determining where species can survive and how they allocate resources. Animals would have evolved behaviors timed to ring light availability or ring shadow presence. Migratory patterns might follow shadow boundaries. Nocturnal species might be more common in regions where ring light makes night navigation easier. Diurnal species in high latitudes might have adaptations for surviving the darker conditions during ring-shadowed winters. Humanity's development would have been shaped by the rings as well, not just culturally, but practically. Early humans spreading out of Africa would have encountered different ring appearances as they migrated, which might have influenced migration routes, settlement locations, and the development of early astronomy. Different human groups might have developed different mythologies and cosmologies based on how the rings appeared from their particular latitudes. The scientific revolution, when it came, would have been influenced by the rings' existence. Early astronomers would have had a readily available example of orbital mechanics to study. The rings don't move relative to Earth, but their position relative to the Sun changes throughout the year, and the Moon moves across them, providing clear evidence that objects in the sky follow predictable patterns governed by understandable laws. This might have accelerated the development of physics and astronomy, or it might not have, depending on countless other factors. History is difficult to predict even when you know all the variables. In modern times, with spaceflight and advanced telescopes, the rings would be a focus of intense study. We'd send missions to sample ring material, fly through the rings, map their structure in detail. We'd understand them far better than we understand Saturn's rings, simply because they're so much closer. Every university with an astronomy department would have researchers studying Earth's rings. Every space agency would include ring research in their mission planning. The rings would be part of the common knowledge of anyone educated in science, as familiar as the periodic table or the theory of evolution. And in popular culture, the rings would be iconic. They'd appear in movies, television shows, video games, and advertisements. The image of Earth with rings would be instantly recognizable, used to represent home, peace, beauty, the uniqueness of our world. Science fiction stories would use Earth's rings as settings, backdrops, even plot elements. The rings would be inescapable, woven into the collective consciousness of humanity, as fundamental to our self-image as the fact that we live on a planet with oceans and continents. This is what rings would mean for how we understand ourselves and our place in the universe. They'd be a feature that makes Earth even more special, even more worth protecting, even more beautiful from a cosmic perspective. They'd be a reminder that we live in a universe capable of creating such structures, where the same gravity that holds us to the ground also creates rings, orbits planets around stars, and stars around galactic centers, connecting everything through the same fundamental force. And on quiet nights, when you look up and see the rings glowing softly against the darkness, all of that context would be there in the background of your mind. The physics, the poetry, the history, the science, the beauty. All of it contained in that gentle arc of light crossing the sky, permanent enough to seem eternal, temporary enough to be precious, real enough to touch if you could reach high enough, which we can now, with our spacecraft and our technology, and our endless curiosity about the world above us. But let's bring this back down to Earth, literally. Let's talk about something immediate and sensory. What would it feel like to experience specific moments with rings present? Not the general long-term cultural effects, but specific, immediate experiences. A sunrise, a storm, a quiet moment alone under ring light. These small, personal experiences would accumulate over a lifetime to create a relationship with the rings that's different for every person, but universally human. Dawn is approaching. You're standing outside, maybe on a balcony, maybe in a field, somewhere with an open view of the eastern horizon. The sky is still dark but beginning to brighten. Stars are visible, though fading. And above you, stretching across the southern sky if you're in the northern hemisphere, the rings glow faintly, catching sunlight that hasn't yet reached you on the ground. The rings are brightest near the eastern horizon, where they're most directly illuminated by the approaching sun. As you watch, the glow intensifies. The ring band becomes clearer, more defined. You can see structure now, darker lanes within the brightness, subtle variations in color from white to very pale blue. The light is cold, not warm like sunlight, but pure and clean, reflected from ice crystals 1,000 kilometers or more above your head. Then the sun breaks the horizon. The sky blazes orange and red near the sunrise point. The rings, where they pass near the sun, wash out in the glare. But away, from the sun toward the north and south, the rings remain visible, now shining gold and orange, colored by the same atmospheric scattering that colors the sunrise itself. They're beautiful in a way that photographs can't quite capture, because the full dynamic range of the scene exceeds what cameras can record. Your eyes adapt, seeing detail in both the bright sunrise and the glowing rings simultaneously. As the sun rises higher, the rings fade from visibility in the daytime sky. They're still there, still reflecting sunlight, but the brightness of the day sky overwhelms them. By the time the sun is fully risen, the rings are invisible except as a very faint, subtle band if you know exactly where to look, and the sky is very clear. You go about your day and the rings are absent from your awareness, hidden by daylight. Later, a storm is approaching. You see it on the western horizon, dark clouds stacking up, the air heavy and still. The sun is behind the clouds, turning them silver and gray. And above the clouds, where the sky is still clear, the rings cut through, a bright line against the darkness. The contrast is striking. The storm threatening below, the rings serene above, both part of the same atmosphere, but on vastly different scales. As the storm moves closer, the rings disappear behind clouds. Rain begins. Lightning flashes, illuminating the clouds from within. Thunder rolls across the landscape. The storm passes over you, wind and rain and electricity, primal and powerful. And then it moves on, heading east, leaving clean air and wet ground behind. You look up. The clouds are breaking. Patches of clear sky appear. And there, visible again, the rings shine through the gaps, water droplets on their particles reflecting sunlight, unbothered by the storm that just passed thousands of kilometers below them. The rings are constants. Weather happens beneath them. They're above all of it, permanent on human timescales, indifferent to the chaos of atmosphere and surface. Evening comes. You're in a city now, buildings and lights, the sky above limited to the gaps between structures. The rings are visible, threading between buildings, a natural feature cutting through human construction. Street lights are coming on. Cars pass by. People walk past, heading home or heading out, most of them not looking up, focused on their immediate surroundings. But you look up and you see the rings, and for a moment you're reminded of scale, of the fact that above this city, above this planet's atmosphere, there's a structure so large that it spans hemispheres, yet so thin that you could fly through it in seconds if you had the means. Later still, much later, you're outside the city. Maybe camping, maybe just in a rural area with less light pollution. The moon is absent, in its new phase, somewhere between you and the sun, invisible. The stars are brilliant. The Milky Way is visible as a faint band of light stretching across the sky. And the rings, the rings are spectacular. They're fully illuminated at this time of night, catching sunlight from below Earth's horizon. They're bright enough to cast shadows, faint but detectable. Your shadow on the ground is a soft, diffused thing, with no sharp edges, because the rings are an extended light source, not a point source like the sun or a small disk like the moon. The shadow is barely darker than the surrounding ground, but it's there, and it moves as you move, your personal connection to the light from 10,000 kilometers up. The rings themselves show detail. You can see the brighter regions and darker regions clearly. You can see what might be gaps, thin dark lines cutting through the brightness, though you'd need a telescope to confirm whether you're really seeing gaps or just lower density regions. The rings seem three-dimensional, not flat, because of the way brightness varies across their width. They have depth, texture, structure. You lie down on the ground, looking straight up. The rings arc overhead, a grand sweep from one horizon to the other. Following the arc with your eyes, you feel the curve of it, the geometry, the way it divides the sky into two halves. The stars on one side, different constellations on the other, separated by this band of light that's both natural and impossible seeming. You think about the fact that you're on a planet, not just conceptually, but feeling it. The rings make Earth's planetary nature obvious. You're on a ball of rock, spinning, orbiting the sun, and around your planet there's this structure, this ring system, held in place by nothing but gravity and motion. It's vertiginous for a moment, the sense of being on a world, not just standing on ground, but standing on a curved surface suspended in space. The rings make it real in a way that's harder to achieve without them. Time passes. You might fall asleep out here under the rings and stars. If you do, you sleep well. The ring light gentle and unobtrusive. Not bright enough to disturb sleep, just bright enough to keep the darkness from being absolute. When you wake, hours later, the rings have changed. Earth has rotated, carrying you eastward, and the ring's illumination has shifted. The western part of the arc is darker now, entering Earth's shadow. The eastern part is brighter, catching sunlight more directly. The pattern is different than it was, though the rings themselves haven't moved at all. Only your position has changed. Eventually you return home, return to daily life, return to responsibilities and routines. The rings fade back into background awareness. You don't think about them constantly. You don't spend every evening outside staring at them. They're just there, part of the environment, as familiar as walls and doors and furniture. But they've shaped you, in small ways, the cumulative effect of thousands of glances upward, hundreds of deliberate observations, dozens of moments like this one when you stopped and really looked and let yourself feel the wonder of living on a ringed world. And that would be true for everyone. Every person growing up with rings would have their own collection of ring memories, their own favorite views, their own meaningful moments, their own personal relationship with this feature of the sky. And collectively, billions of people's individual experiences would create a shared cultural understanding of what rings mean, how they make people feel, why they matter beyond their scientific interest. This is what rings would be like to live with. Not just a visual phenomenon, but an experiential one. Not just something to study, but something to feel. The cold light on your skin during ring bright nights. The shade when ring shadow passes over during a summer day. The beauty of sunrise when rings catch the light before the ground does. The constancy of knowing that wherever you go, if the sky is clear and you're at a latitude where rings are visible, you'll see them, always in the same position relative to the horizon from any given location. Always there, always real. We're nearing the end of this exploration now. We've covered the science, the appearance, the effects, the implications, the experiences. We've built a comprehensive picture of what Earth with rings would be like using only verified physics and established observations from other ringed planets in our solar system. Everything described is possible, realistic, based on actual measurements and known principles. None of it is fantasy or speculation beyond the initial premise that rings exist. So let's bring this journey to a close with some final reflections on what this thought experiment tells us about Earth, about rings, about the nature of planetary systems, and about the value of imagining things that don't exist in order to better appreciate what does exist. Earth doesn't have rings. That's the reality. When you look up, you see sky, clouds, sun, moon, stars, planets, but no rings. Earth is the third planet from the Sun, a terrestrial world with one large natural satellite, a magnetic field, a substantial atmosphere, and a surface covered in water, rock, ice, and life. No rings. They're not there. They never have been, as far as geological evidence shows, but they could have been. The physics that creates rings works here just as well as it works at Saturn. Earth has sufficient mass, sufficient gravitational pull, a suitable environment for rings to form and persist for geologically significant timescales. The only missing ingredient is the material, orbiting in the right place, ground down to the right size. That's an accident of history, not a fundamental constraint. This tells us something important about planetary systems. They're contingent. They depend on specific sequences of events, particular impacts, particular captures, particular orbital resonances. Change any one event in Earth's history, and you might have a very different solar system today. A different number of planets, different orbital configurations, different moons, and yes, possibly rings around worlds that currently have none. Saturn's rings might not last forever. In a few 100 million years, they might be gone, and Saturn would be a ringless gas giant. Still massive, still beautiful with its bands and storms, but lacking that iconic feature that makes it instantly recognizable. Jupiter already has only faint rings. Uranus and Neptune have dark, narrow rings easily overlooked. In a billion years, all four gas giants might be ringless, and if humans or our descendants are still around, they might look back at old photographs and marvel that there was a time when ringed planets were common in our solar system. Conversely, new rings might form. Jupiter's moon Io is volcanically active, constantly resurfacing itself with lava. That material comes from tidal heating, energy pumped into Io by gravitational interactions with Jupiter and other moons. Io is slowly spiraling inward, very slowly, losing energy to tidal friction. In millions of years, it will cross Jupiter's Roche limit and break apart, creating spectacular new rings. Observations from multiple spacecraft have confirmed this process is occurring, just very gradually. So planetary systems evolve. They change, rings come and go, moons are destroyed or formed, orbits shift. Nothing is permanent except on timescales too long for planets themselves to last. Eventually the sun will exhaust its hydrogen fuel, expand into a red giant, and engulf the inner planets, including Earth. No rings at that point would matter, no Earth would remain. But that's billions of years away. In the present, Earth is a stable, beautiful, complex world, home to an incredible diversity of life, orbiting a stable star, protected by a magnetic field and atmosphere, shaped by tectonics and water and weather into constantly changing landscapes. It's remarkable without rings. Adding rings wouldn't make Earth more worthy of preservation or more important. It would just make it different. The value of this thought experiment isn't to suggest Earth would be better with rings. It's to help us see our planet more clearly by imagining it differently. When you change one major feature in your mind, all the connections between that feature and everything else become visible. Climate, tides, orbital mechanics, cultural development, space exploration, all these things connect to ring presence or absence, and by tracing those connections, we understand Earth's actual system better. We understand how important the Moon is, for instance. Our Moon is unusually large for a terrestrial planet. It creates significant tides, both in the ocean and in Earth's rock, and those tides have influenced evolution, geology, and climate. The Moon stabilizes Earth's axial tilt, preventing it from varying wildly over time as Mars's tilt does. This stability has kept Earth's climate relatively stable, which may have been necessary for complex life to evolve. No moon or a different moon might mean a different Earth, possibly one without beings capable of asking these questions. Similarly, we understand how important the absence of rings has been for space exploration. The satellites we've launched, the space stations we've built, the missions to the Moon and beyond, all of these were simpler because Earth lacks rings. We didn't have to navigate through debris fields. We didn't have to shield spacecraft against constant particle impacts. We didn't have to avoid crossing the ring plane on every launch. The absence of rings made space more accessible. But absence isn't the same as void. Lack of rings doesn't leave a gap in Earth's nature. Earth is complete as it is. Adding rings would add something new but wouldn't fill a missing piece, because there's no missing piece. This is a key insight. Planets are what they are, shaped by their histories, complete in themselves. We can imagine them. Different, but the imagined difference doesn't make the reality incomplete. What this exploration has hopefully provided is a sense of wonder at planetary systems in general. Rings are real. They exist. We've seen them, measured them, flown spacecraft through them. They follow understandable physics. They're not magic or mystery, but natural consequences of gravity, orbital mechanics, and the material properties of ice and rock. And yet, they're beautiful. The physics explains how they work, but it doesn't diminish the aesthetic impact of seeing them. The same is true for Earth as it exists. Understanding how Earth's atmosphere scatters light to create blue skies doesn't make sunsets less beautiful. Knowing that the Moon is a dead rock following Newtonian mechanics doesn't make moonrise less moving. Understanding plate tectonics doesn't make mountains less majestic. Knowledge and wonder coexist perfectly. In fact, knowledge often enhances wonder by revealing the depth and complexity beneath surface appearance. If you were to look up tonight and see rings in the sky, knowing everything you now know about what they are and how they work, they would be more impressive, not less. You'd see not just a pretty arc of light, but a dynamic system of billions of orbiting particles, a temporary structure maintained by precise balance of forces, a visible demonstration of orbital mechanics, a connection between the ground where you stand and the vacuum of space thousands of kilometers up. The knowledge adds layers of meaning, and when you look up tonight and see no rings, just stars and perhaps the Moon and the planets if they're visible, that too should inspire wonder. You're looking at a sky that's been essentially unchanged for millions of years. The stars are the same stars ancient humans saw, arranged in the same patterns. The moon follows the same path. The planets wander through the zodiac as they always have. The consistency, the reliability of the night sky is itself remarkable. Earth is the only home we've ever known. For the entirety of human history, for all the thousands of generations of humans who've lived and died, Earth has been the setting for everything. Every achievement, every tragedy, every moment of joy or sorrow or boredom or excitement, all of it has happened here, on this planet, under this sky. Rings or no rings, Earth is precious. Rings or no rings, the universe is vast and we are small. Rings or no rings, existence is strange and wonderful and worth contemplating. So as you settle in tonight, as you let yourself relax, as you allow your thoughts to slow and drift, remember that the universe is full of possibilities. Ringed planets exist. Ringless planets exist. Planets with life exist, at least one, probably more scattered across the galaxy. Planets with intelligent life exist, at least one, possibly more. The cosmos is diverse, complex, governed by understandable laws but producing endless variation within those laws. Earth is one expression of those laws, one outcome of one particular sequence of events. And it's beautiful, it's enough, it's home. Whether we imagine it with rings or see it as it truly is, Earth remains the place where we live, the world that sustains us, the planet that, through billions of years of cosmic history, gave rise to life and eventually to beings capable of looking up, wondering what if, and finding joy in the contemplation. The rings we've explored tonight exist only in thought, but the wonder they inspire is real. The science is real. The physics is real. The beauty is real. And Earth, our actual Earth, with its actual sky and its actual history, is real and remarkable and worthy of all the attention and care and love we can give it. So let your thoughts settle now. Let the image of rings, if you've been holding it in your mind, fade gently. Return to the actual world, the real Earth, the only Earth we have. And know that it's enough. It's more than enough. It's home. Thank you for joining me on this exploration of what Earth might be like with rings. I hope you found it peaceful, informative, and perhaps inspiring. If you enjoyed this journey through hypothetical planetary physics and the beauty of orbital mechanics, I'd be grateful if you would like this video and subscribe to Nebula Nights. There are many more cosmic topics to explore together, many more quiet investigations of the universe's wonders, many more calm conversations about the nature of reality and the places we might go, in imagination, if not in body. Until next time, look up, wonder, and rest well under whatever sky you find yourself beneath.